Okay, folks, we are on section 6.3, and section 6.3, um, section 6.3 is area of triangles. Now, I know what you're thinking, Mr. Francis. Come on. I've had geometry. I know that the area of a triangle is 1/2 base times height. And that's great that you know that. I'm proud that you know that. But here's my question to you. What if you don't know the height? Can you find the area of a triangle without knowing the height? And the answer is yes. So let's just look at this triangle here. This is side B. This is side A. This is angle theta. And we'll say this right here is the height. Well, since we have a side, an included angle, and a side. So side, angle, side. Because of that, we can actually solve for the area of a triangle without ever knowing the height. Here's how. All right, so watch. The sine of angle theta is what? In this particular right triangle, sine is opposite over hypotenuse. So h over a. So if I solve for h, that is sine theta times a, or the most popular way to write it is a sine theta. So if I take that and I substitute it in for h, what I really get here is AB divided by 2 times sine theta. So notice, I've taken our original area formula. I've gotten rid of the height. I don't have to know the height anymore as long as I know a side, an included angle, and a side. So side, angle, side. So this is going to make finding some areas a little bit easier for you. So for instance, if we have this triangle here, if we say that this is 35 degrees and we know this side is 8 meters and this side is 5 meters. What is the area of this triangle? Well, we don't know the height, so the area is going to be 8 times 5 divided by 2 times the sine of 35 degrees. Make sure your calculator's in degree form. And punch this out in your calculator. And you could type this as 1/2 times 8 times 5 times sine 35. I just like writing it like that. But you could pull the 1/2 out in front. And it's going to be 11.5. And since these were meters and area is in square units, this is going to be square meters. Now I know that seems almost too easy, doesn't it? Compared to some of the stuff we've done this semester, but that's about as easy as it gets, okay? So, suppose we don't have the included angle. Suppose that we have 3 sides. Well, that's where Heron's formula comes in. And this is Heron's formula. Heron is a Greek philosopher and mathematician. A lot of these Greek philosophers were also mathematicians, and so they just kind of went hand in hand back in the day. And what he basically did is he found a way to actually solve for the area of a triangle without knowing the angles, just by knowing 3 sides. So here's our triangle. And notice it's not a right triangle or anything special. This is alpha, beta, gamma. So this is C, A, and B. So we have something called the semi-perimeter. Heron developed something called the semi-perimeter, which we denote with the letter S. So what he says, the semi-perimeter equals the perimeter of this triangle divided by 2. The perimeter divided by 2. And once you find that, then you can use Heron's formula to find the area. And what Heron's formula is we find the area by taking the square root of the semi-perimeter times the semi-perimeter minus A times the semi-perimeter minus B times the semi-perimeter minus C. And that will give us, that's Heron's formula, and that will give us our area. Now, Heron's formula is obtained from the area formula using some half-angle identities and that sort of thing. It's a very complicated proof for Heron's formula, but it is on page 379 in your book. I definitely don't have room to do it on the video, but if you look over page 378, 379, and 380, that's the whole proof. I don't expect you to know how to do the whole proof. It takes a lot of getting used to be able to understand it. Okay, but if you can read through it and understand it a little bit, that's great. That's great. But just like most of these, in this latter part of the class, we're not really concerned as much with the proof of it as much as with the application of it. So I'm not going to take up video time with that. But if you have questions on the proof, feel free to ask me. I'll try to help you understand it the best I can. You know, it's one of those things that just takes practice with looking at it over and over and over and over to understand it. And to be honest with you, the first time I took trig, I didn't really understand it either. It wasn't until I got into advanced calculus in college and that should tell you something. The first time I actually proved this was in advanced calculus in college, and so that was in graduate school. So you know it took a while to even get to where we even proved it in class, and so that I understood it at that point after advanced calculus. But it's okay if you don't understand everything about the proof of it. Okay, so don't let that bother you in terms of the application, because the application of it, as you can see, is very, very easy. So don't let that bother you. So let's look at an example of this. So let's find the area of a triangle that has sides listed as follows. A equals 12.0. B equals 8.0, and C equals 6.0. Alright, so first things first, let's find the semi-perimeter. So that's going to be 12.0 plus 8.0 plus 6.0 divided by 2. Okay, so that should come out with 13.0. 3 significant digits once you're done. Now that's the first step. Then, the way I like to do this, folks, I like to do it like this. I like to find these individual parts first before I place it under the root, because these individual parts, if you start placing it under the root, it can get kind of jumblesome. So I like doing this first and saying, okay, 13.0 minus 12.0, which is 1.0, 13.0 minus 8.0, which is 5.0, and 13.0 minus 6.0, which equals 7.0. So I like to do that first, then do the area. So now I can find the area quite simply. So it's S, which is 13.0, times S minus A, which is 1.0, times S minus B, which is 5.0, times S minus C, which is 7.0. Punch all that out in your calculator, and you should get 21 square centimeters. If all these are in centimeters, by the way, I didn't write it, but that's how I knew it was square centimeters. I didn't just make that up. Okay, all these are in centimeters, so that's square centimeters there. All right, so as you can see, the application of it is fairly straightforward. Now, notice what we've had. If we had side angle side, we could very easily use the basic area formula to solve this. If we had three sides, we could use Heron's formula to solve for the area. But what if you don't have SAS, and what if you don't have three sides? How do you solve for the area of a triangle? Well, basically it goes to this. What you have to do is you have to use your rules of law of sines, law of cosines, to find the area, to find the parts of the triangle that you need to be able to fit into one of these area formulas. For instance, if I ask you to find the area of a triangle that has alpha 39 degrees, A equals 9.4 feet, and B equals 7.2 feet. Alright, well, think of our triangle. So alpha is 39, this is beta, this is lambda, excuse me, not lambda, but gamma. This would be A, this would be B, which would be 7.2. And we don't know beta. Well, notice what we have here. I have a side and a side. So if I knew that angle right there, we could use this basic formula here. And AB divided by 2 sine theta. We could use that to find our area if we knew gamma. Well, we can find gamma because we have alpha, we have A and B, so I could actually use my law of sines here, and I could find beta. Now, I know what you're thinking. Mr. Francis, you said gamma. Well, why am I finding beta first? I'm finding beta first so I can say 180 minus alpha plus beta, because that's actually going to give me our angle gamma. So that's why I'm trying to solve beta first. So we know sine alpha, that's 39, over A, which is 9.4. Sine beta over B, which is 7.2. So if we solve for sine beta, we get sine beta equals 7.2 times the sine of 39 degrees all over 9.4. And so we can do the inverse sine. To get our angle beta. Use our inverse sine. And so once you do that, you should get 29 degrees here. Now, once you have that 29 degree mark, we can subtract, say, 180 minus 39 plus 29 to get our gamma. So in this case, gamma is going to be 112. Gamma is going to be 112. So now we know gamma. We have the two sides, so this is a side angle side now. So we can plug in our area formula. 7.2 times 9.4 divided by 2 times the sine of 112. And because this is area, you should get 31. And this is feet, so it's going to be square feet. And that's how you get your answer there. Okay, so now, why did I choose beta first instead of trying to just go straight? I could have tried to use the law of sines here, just like I did here. I could have tried to use it to solve for gamma first, but I didn't have side C. And number two, I already knew alpha was this. And look, alpha is bigger than beta. So typically what that means is that angle beta is going to be smaller than angle alpha. So you know beta is going to be acute, which it is, and it's smaller. So it gives you the two acute angles so that you can get the obtuse one here. So it kind of, you use a little common sense with that, okay, about the sides being shorter than one another and that sort of thing. That's going to help you with these problems and make it a lot easier and make this so that you do very, very well. I'm expecting all of you to do very, very well on this particular quiz, okay? So that's all of section 6.3. Y'all have a great day.